Hello everyone. Let us move to the next category: causal, anti-causal and non-causal signals. Let's see what exactly these signals are. As you can see, we have three columns. In the first column, we have given some information about causal signal. In the second column, we have given information about non-causal signal. And in the third column, we have given information about anti-causal signal. So a discrete time signal is said to be causal if it is finite or defined for n greater than equal to 0 and is 0 for n less than 0. That means a discrete time signal which has some value, or you can say which has some amplitude, or you can say which has some samples for n greater than equal to 0, and 0 value, or you can say it doesn't have any value for n less than 0, any information for n less than 0, then only I can say that the signal is a causal signal. Now let us see what exactly a non-causal signal. A discrete time signal is said to be non-causal if it is finite or defined for either n less than equal to 0 or for both n less than equal to 0 and n greater than 0. That means doesn't matter a signal is defined for n greater than 0. If it is defined for n less than equal to 0, then I can say that that particular signal is a non-causal signal. Now let's see what exactly an anti-causal signal. So basically, a discrete time signal is said to be anti-causal signal if it is finite or defined for n less than equal to 0 and 0 for n greater than 0. Okay, so this is anti-causal signal. So one can easily visualize the difference between non-causal and anti-causal signal. Look at here, we don't have any sample for n greater than 0 in anti-causal, but we can have some samples for n greater than 0 in case of non-causal. So I can say that all anti-causal signals are non-causal, but not all non-causal signals are anti-causal. This is the only difference between non-causal and anti-causal. Now, causal signals are signals that are 0 for all negative times. The same definition in different form. All negative times means n less than 0. So a causal signal is always have 0 samples for n less than 0. Non-causal signals are signals that have non-zero, or you can say finite values in negative times, but it may or may not have finite values in positive times. An anti-causal signals are signals that are 0 for all positive times. Okay, we should not have any amplitude for the positive time axis. Now a causal signal can also be called as right side sequence, or you can say right side signal. Why? Because as we discussed in the first definition, that a causal signal has amplitude or samples for n greater than equal to 0. So any sample which is placed for n greater than equal to 0 comes in the right side of the axis. That is why it is called right side sequence. Now an anti-causal signal also can be called as left side sequence, because all the samples in case of anti-causal signal is placed on the left side of the origin. Now a non-causal signal can also be called as both side sequence and can also be called as left side sequence. As I told you already that all the anti-causal signals are non-causal, that is why a non-causal signal can be called as both side sequence, because we can have samples for n less than 0, we can also have samples for n greater than 0. That is why it can be a both side sequence or two-sided sequence. So we have few examples over here. Under the causal, look at here. The first example is x of n equal to 2, 3, 4, 5, 7, and arrow mark is under the first sample. That means I can say this is a right side sequence because all the samples are present in the right side of the origin. We do not have any sample in the left side of the origin. Okay, or you can say for the negative time axis. So this particular signal is a causal signal. Now look at here, under the non-causal, x of n equal to 2, 3, 4, 5, 7, and here we have an arrow mark or pointer under 4. So we have some samples on the left side of the origin as well as on the right side of the origin. That is why this particular signal is called as non-causal signal. So now in the example under anti-causal, you can see the same set of samples are given, but this time the pointer is at the last sample. Okay, so I can say that we don't have any sample for n greater than 0, but we have some sample for n less than equal to 0. So I can say this particular signal is an anti-causal signal, and this can also be called as non-causal signal. Now second example is x of n equal to del of n minus k. So basically del of n is a unit impulse function, and del of n is always equal to 1 for n equal to 0 and is equal to 0 otherwise. So del of n minus k is a time delay operation, and whenever you want to plot del of n minus k, basically the del of n will get shifted, the sample of the del of n will get shifted by k unit to the right of the axis. So one can say that del of n minus k is a causal signal because we do not have any sample on the left side of the origin. Now x of n equal to cos omega n. Okay, basically cos omega n is an infinite duration sequence, and it extends towards minus infinity as well as towards infinity. So that is why cos omega n is a best example of a non-causal signal. Now cos omega n u of minus n. As we know that u of minus n is a time reversal operation of u of n. That means all the samples will be shifted from the right side of the origin to the left side of the origin. So basically whenever a cos function will get multiplied with u of minus n, all the samples of cos will be present in the left side of the origin, and right side of the origin we do not have any sample. So this is going to be a best example for anti-causal signal, which is also called as non-causal signal. Now under the causal we have one more example, x of n equal to cos omega n u of n. As we know that unit step function u of n is a causal signal, and whenever cos omega n will be multiplied with u of n, all the positive part of the cos function will appear on the graph. So this is all about the differences between causal, non-causal and anti-causal signal. And we have put a note here that all anti-causal signals are non-causal, but not all non-causal signals are anti-causal. So till now we have discussed the causal, anti-causal and non-causal with some definition and with some examples. Now for better understanding, we have plotted a graph over here, and with the help of graph you can see that why it is called a causal signal. So we know that causal signals are signals that are 0 for all negative times. Now we have one signal x of n equal to 1, 2, 5, 7, 0, 1. And as we do not have any pointer over here, I can say the first sample or the extreme left sample is the sample at origin. The moment I will plot this particular signal on the graph, we can say at 0 it is 1, at 1 it is 2, at 2 it is 5, at 3 it is 7, at 4 it is 0, and at 5 it is 1. Now you can see that we have samples for n greater than equal to 0, but we do not have samples for n less than 0. That is why this particular signal is called a causal signal. So this is my negative time axis, this is my positive time axis. You can also see here is that all the samples are present on the right side of the origin, or you can say positive time axis. That is why this particular signal is also called as right side sequence. So one graphical representation of an anti-causal signal is x of n equal to 1, 2, 5, 7, 0 and 1. Now pointer is at the last sample. So this is the graphical representation for the given sequence. Now you can see that all the samples are available here for n less than equal to 0, but we don't have any sample for n greater than 0. That is why this particular signal is called as anti-causal signal. And as we discussed already, that all anti-causal signals are non-causal because we have samples for n less than 0. So this can also be called as non-causal signal. So here it is, non-causal signal. Non-causal signals are signals that have non-zero value, or you can say finite values in negative times, but may or may not have finite values in positive times. So it is not compulsory that we will be having positive samples for n greater than equal to 0, but we must have some samples for n less than 0. So you can see this is 1, 2, 5, 7, 0, 1. The same set of samples is given over here, but this time the pointer is at 5. So you can see we have some samples for negative time axis but we also have some sample for positive time axis. So this particular signal is called as non-causal signal. But we can't say this particular signal is an anti-causal signal because we have some sample for positive time axis also. So here are a few graphical representation of standard signals. For better understanding, you can see that this is a unit step signal, which is a causal signal, as all the samples are for n greater than equal to 0. This is a cos omega naught n, and it is extended over minus infinity to infinity. So this is 100% non-causal signal, but not anti-causal. The last one is u of minus n minus 2. That means it is a folding plus shifting of u of n. Okay, so whenever a signal is folded, all the samples of positive x-axis will move to the negative x-axis. The moment we shift the folded signal to the -2 or negative quantity, the signal will move left. So you can see the samples are available here for the negative time axis. So we can say this is a 100% anti-causal signal. At the same time, it is also called as non-causal signal. So this is all about causal, anti-causal and non-causal signal. So here in this particular session, in the upcoming lecture, we will discuss about the rest of the classifications of discrete time signals. Thank you.